So here we're going to finish our calculation of magmatic density. Here are the entries we made last time in the prior video, part 1, silicon titanium. We've finished it off for aluminum, iron oxide, magnesium. Iron is 0. We have an entry for iron, but iron is not reported, but we do have the equation there in case we ever want to enter a ferric iron value. We do have ferrous iron. That's how all the iron is reported, so we'll just treat it that way, even though it's probably not that way in real life. There's no function for manganese. We could probably just delete that column if we wanted to. It's not really going to help us any further. And then magnesium, calcium, sodium, potassium. I've left off lithium because no lithium oxide is reported. P2O5 is blank because we have P2O5 reported, but there's no Xi value here. We do have this sodium aluminum term and then water. Let's do water first. Water is not contained here, but the dissolved water content, this is not water as bubbles, but water that's dissolved in the liquid, does have a set of coefficients that are published in Ochs and Lange. I think I said Feldstein and Lange, but they did a study of high potassium volcanic rocks in the southern Sierra Nevada. So strike that. It's Ochs and Lange, 1999. They provide the coefficients here, and these are the same coefficients that we've been using here, and we'll use it in the same equation. So we'll just enter this together. In Ochs and Lange, they report a value of 22.89, so for the molar volume. So we'll take water and multiply it by the quantity of 22.89. That cubic centimeter per mole value is for 1273 K in 1 bar, not 1673. So when we add the dV/dt, the correction here is 0.00946. We're going to multiply that not by this difference in temperature here, because it's not minus 1673, but it's the temperature minus 1273. So we'll take this temperature, add to that 273.15 to make it Kelvin, and then subtract 1273.15 because that's our reference temperature. I'll close the parentheses just to get us back over here, but we do have to add one last coefficient. So we have plus dV/dP, which is a minus 0.000315. So that's the coefficient, and it's multiplied by the pressure minus 1 bar when pressure is expressed in bars. So there is our coefficient for H2O. So let's just check that we've added all this correctly. I'm going to add some parentheses in here to make sure we capture that difference. Otherwise, calculation is not going to work. That looks a little bit better. All right, this looks like sodium minus aluminum. These are normally Margulies-like parameters, so it's not necessarily a subtraction. These are more often multiplication. The dash means the sodium is interacting with aluminum. We usually take the product. I think that's the case here. We're going to assume it's the case here. So we'll take sodium times aluminum, and then we will multiply that. So this is our Xi here. And then we're going to multiply it by, well, nothing over there or there. We just have the pressure correction of 10.18 times 10 to the minus 4. And then we have to multiply that by our difference in pressure. And then we have, we need to close the parentheses. So we will, no, we just need to get rid of this parenthesis here. Add that one. Now we have a correction for sodium interacting with aluminum. Now we take the sum of those. That would be the volume if we had, this is volume in cc per mole, but we had everything multiplied by 100 here. I didn't finish my statement. This would be the volume. We write it as total, but it's really the volume in cc per 100 moles, and what we really want is the volume in cc per mole, and so we just take that whole thing, divide it by 100. You don't have to do that correction if you have cation or mole fractions instead of mole percents. So if you have all of these summing to 1, then you don't have to make that correction. But here we had it as mole percents. We're going to use the percent value. So we have molar volume per 100 moles, and we're going to divide it out by 100, so we have volume in cc's per mole. Now we want density, so we're going to have to make one final correction. The density is going to have units of grams per cubic centimeter. We have volume, which is in cc's per mole, cubic centimeters per mole. So we need is the molecular mass, which is grams per mole. And then we could take the molar mass divided by density, by the volume, and that will give us the density. The moles will cancel out. So how do we get the molar mass? Well, we can take our mole proportions, and I'm just going to take all of these oxide labels here and then copy them and paste them over here. And then I'm going to take, we don't want to shift it down a row. We will take each of these values here, multiply them by their molecular weight. That'll give us grams per, in this case, 100 moles. So for the total here, this is the molecular mass per 100 moles. So what we want is the mass per single mole. So this total here, and we'll just change it to m. This is grams per 100 moles. And we just want grams per mole, so we'll take that divided by 100. So that is 61 grams per mole. And then for the density, we can simply take the molar mass, divide it by the volume, and we have grams per cubic centimeter. So in this case, for a system that has this liquid composition, 28% water, and is at 2 kilobars and 1,000 degrees centigrade, then our estimate for the density is 2.29 grams per cubic centimeter.